All right, section 6.2 is standard units and areas under under normal standard distribution. So when we talk about normal distribution, standard units are really just ways that we can create normal distributions through any type of distribution here. So normal distributions actually do tend to vary in a couple of ways. So the mean can be located anywhere on the x-axis. That's one way that they can vary. Also, the bell shape, the bell curve, is another big indicator in the variation of a normal distribution. Sometimes, depending on the standard deviation, the bell shape may be taller and more skinnier, or more spread out, depending on the standard deviation. Remember, the larger your standard deviation is, the more varied your data is from the mean, the larger your curve is going to be. The smaller your standard deviation is, the more condensed your data will be, which will lead to your data being more condensed. Now, the differences among the normal distributions cause difficulties when we try to compute that area underneath that curve. So remember, area underneath that curve is the probability that a measurement will fall into a specific interval. Now, there is a way that we can standardize these normal distributions so that we can compare them in a more streamlined method. So in order to standardize the distributions so that we can use one table of areas, what we need to figure out is how many standard deviations away from the mean a measurement lies. So in this way, what we're really doing is we're comparing a value in one normal distribution with a value in a different normal distribution, using a standard unit, a standard method here. So here's how we do this. Okay, so here's an example. Suppose Tina and Jack are in two different sections of the same course. Each section is quite large, and the scores of the midterm exams of each section follow a normal distribution. In Tina's class, the average was 64, and her score was 74. In Jack's section, the mean was 72, and his score was 72. So both Tina and Jack were pleased that their scores were each 10 points above the average of their respective section. However, it doesn't really tell us how much they did with respect to the other students in the section. Now, these are two different normal curves. So Tina's section, in Tina's class, the 74 above her 64 may not mean the same as Jack's 82 over the average of 72. So for example, here is Jack's section, and here's Tina's section. With Jack's section, the standard variation is larger, meaning that the data is more spread out. So, Jack having an 82 might be a little bit more, might be not as exciting as Tina with her 74, because 74, her 74, much of the data is, closer to 64. So Tina might actually be more above average in her scores than Jack's is. So Tina's 74 was higher than most of the other scores in her section, while Jack's 82 is closer towards the average. Therefore, Tina's score is actually far better with respect to her class than how Jack did. Now, the question is, this situation demonstrates that it's not sufficient to know the difference between the measurement and the mean, okay? You need to know the distance that measure is in standard deviations from the mean. So we need to consider the spread of the curve. We need to consider the standard deviation. So what we're really trying to do is we're trying to figure out how many standard deviations a measurement is away from the mean. This is known as a z-score. A z-score, also known as a standard score, is the number of standard deviations between the original measurement and the mean. So the way that we figure this out is the number of standard deviations between the measure and the mean. It's the difference between the measurement and the mean divided by the standard deviation. In other words, here's the formula to calculate what's called the z-score. You take your measurement, you subtract the mean, and you divide it by the standard deviation. So the mean is a special type of distribution, or not a special type of distribution. It's a special value of that distribution. So if our measurement is the mean, watch what happens. So here's the formula to calculate the mean. If our measurement is the mean itself, well, anything minus itself is 0, the z-score is 0. So what this means is that the mean is 0 standard deviations away from itself. And of course, you can see that when you look at a normal curve because the mean is right in the middle. It's right in the middle of the curve. Okay. Now, because we're subtracting, there is a possibility we could have a positive and a negative z-score. So if the z-score is 0, then your measurement is the mean. If your x value, if your measurement is positive, if your z-score is positive, that means that your x value is above the mean. If your measurement is below the mean, if your measurement is below the mean, then your z-score would be negative. Now, again, what does this tell us? A z-score of a measurement tells us the number of standard deviations the measurement is from the mean. The closer a z-score is to 0, the closer your value is to the mean. Again, if you have a positive z-score, your measurement is above the mean. If you have a negative z-score, that means your measurement is below the mean. Okay, here's a chart that explains this, right? If your x value is the mean, then your z-score will be 0. If it's greater than the mean, then your z-score will be positive. If it's less than the mean, your z-score will be negative. Now, when we talk about average, when we talk about the mean, okay, when we take the word average here, unless we say otherwise, we're going to take the word average to be either the mean, the sample mean, or population mean, which we've been doing already. So we're just going to keep being consistent with that. When we say average, we're talking about the mean. Here's an example. A pizza parlor franchise specifies that the average amount of cheese on a large pizza should be 8 ounces, and the standard deviation only 0.5 ounces. An inspector picks out a large pizza at random in one of the pizza parlors and finds that it is made with 6.9 ounces of cheese. Assume that the amount of cheese on a pizza follows a normal distribution. If the amount of cheese is below the mean by more than 3 standard deviations, the parlor will be in danger of losing its franchise. How many standard deviations from the mean is 6.9? Is the pizza parlor in danger of losing its franchise? So again, we got to consider our variables here. Our average is 8, our standard deviation is 0.5. So average is 8, standard deviation is 0.5. So how many standard deviations from the mean is 6.9? So 6.9 is our measurement. I want to know what its z-score is in relation to that mean and that standard deviation. So we're going to use the z-score formula. Z equals x minus the mean divided by the standard deviation. That's 6.9 minus 8 divided by 0.5. So let's calculate that. 6.9 minus 8. Divide that by 0.5. I get a z-score of negative 2.2. Now, is the pizza parlor in danger of losing its franchise? The problem says that if the amount of cheese is below the mean by more than 3 standard deviations, the parlor will be in danger of losing its franchise. That means that the z-score cannot be less than negative 3, and it cannot be greater than positive 3. My z-score was negative 2.2. That falls well within 3 standard deviations. So from that, we can safely assume that the pizza parlor will not be in danger of losing its franchise because we're not outside of 3 standard deviations from the mean. Then we have the raw score. Let's say I'm given a z-score, and I want to know what measurement comes from that z-score. Because we've seen how to convert from measurements to standard units, but what about the reverse? Well, we can easily reverse this process by solving for the original raw score, right? So here's my z-score, x minus the mean divided by standard deviation. Well, if I wanted to find what my raw score was, I would just solve for that. So if I multiply standard deviation on both sides, x minus the mean, and then just add the mean. So that gives me this formula. To find the raw score or the original measurement that comes from the z-score, it's the z-score times the standard deviation plus the mean. Find the raw score corresponding to a z-score of negative 1.2 when the mean is 10 and the standard deviation is 2. So here's my z, here's my mean, here's my standard deviation. Put it in the formula. X equals negative 1.2 times 10. No, sorry. Times 2. That's standard deviation. Standard deviation times z plus the mean, which is 10. So this is negative 2.4 plus 10. That is about what, 7.6? That's my raw score. If I were to apply the z-score formula, then 7.6 minus 10 divided by 2 should give me negative 1.2. Okay. Now let's talk about standard normal distribution. So if an original distribution of x values is normal, well then guess what? Their corresponding z values will have a normal distribution as well. And that distribution will have an average of 0 and a standard deviation of 1. The name of this is called a standard normal distribution. A standard normal distribution is a normal distribution with the mean of 0 and a standard deviation of 1. And again, so we talked about your average, 1 standard deviation from the mean, 2 standard deviations from the mean, 3 standard deviations from the mean. In a standard normal distribution, the only change is instead of specific values of x and x minus the, or specific values of the mean and mean minus 1 standard dev or mean plus or minus 2 standard dev, you have your mean at 0, and then you have 1, 2, and 3, negative 1, negative 2, and negative 3 for your standard deviation levels. So the cool thing about a standard normal distribution is that any normal distribution of x values can be converted to a standard normal distribution by converting all x values to z-scores. So anytime that we take a normal distribution and we convert everything to z-scores, we actually are coming up with a normal distribution. And it will always have a mean of 0 and a standard deviation of 1. But what does that tell us? Again, it tells us that the mean is 0, standard deviation is 1, and that any normal distribution can be converted to a standard normal distribution by converting every measurement to a z-score. But now we're going to use this to talk about areas underneath the standard normal curve. So we've seen how to convert any normal distribution to a standard normal distribution. We can go from x value to z-score and z-score to x value. But what's the advantage of this? Well, we have tables that can show us the area underneath a standard normal curve for almost any interval along that axis. Okay, before we get into that, I'll even show you. So in your textbook, and hopefully this will be in your OneNote as well, you have a table of z-scores. So if you want to find the area underneath a normal curve, then you find the z-score, right? Each value on this column is the ones and tenths place. These columns here represent hundredths place. We'll have some examples of that in just a minute. But why is it important? It's because, remember, area underneath a normal curve, whether it's standard or otherwise, is equal to the probability that a measurement of an item selected at random will fall in that interval. Thus, this standard normal distribution can be a tremendously helpful tool, right? Because again, here's your area. There's your 68%. That's the empirical rule. Here's your 95%. Here's your 99.7%. Now, let's talk about using a standard normal distribution table. So before we use this table, okay, we have to find the range of z values for which the areas are given. So, it's usually depicted in a picture that accompanies the table. So in this text, we'll use what's called a left tail style table. This style table gives cumulative areas to the left of a specific z-score. And there are ways that we can calculate any z-score, whether we use the left tail style directly or whether we find the complement or we find a particular area between two z-scores, okay? So before we start, remember, the largest and smallest z-scores on our table is negative 3.49 and positive 3.49. So anything to the left of a z-score that's smaller than this number, we're going to treat as 0. On the other side of that, right, anything to the left of a z-score smaller than 3.49 is 0. Anything to the right of a z-score larger than 3.49, we will also treat as 0. And again, why are we doing this? It's because any area outside this range is less than 0.0002. So it's a very, very small number. It's easier just to estimate. Now, what if the z-score was smaller than this, but we're looking for the area to the right? Well, that just covers the entire curve. And that would be 1. Same thing on the other side of that coin. Now, if you're looking for area underneath a curve to the left of a specified z-value, then we use the table entry directly. So here's your z-score. I find whatever z-score is on that table. And remember, we're talking about this table right here. And whatever number that is, that's the area. So for example, if we find area to the left of z equals 0.29. So if I look on my chart here, my tens place is, my ones and tens place is 0.2. So if I look, that's right here, 0.2. I look for a hundredths place of 0.09. That's all the way out here. That area is, let me make sure I got that right, 0.6141. That would be the area here. Now, if I'm looking for the area to the right of a specified z-value, again, we're using a left tail style curve, which means that the table only tells us areas to the left of that z-value. Well, if I take the area to the left of that z-value and I subtract it from 1, that's the complement. This is the complement here. So 1 minus this gives me the area to the right. So, for example, if I'm looking for the area to the right of z equals 1.34, then what I want to do is I want to find the area to the left of that and subtract it from 1. So 1 minus the area for 1.34. So if I look at my table, I look for 1.3 in that first column. So 1.3, that's about right here. And then I look for 0.04, so 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. That's 0.9099. 9099. So I subtract that. And I get a value of 0.0901. Now, if I'm looking for areas in between two z-values, z1 and z2, well, what I want to do is I want to find the larger area first. And this, I'm assuming that z2 is larger than z1. So find the area of the larger z-value first, subtract the area to the left of the smaller z-value. Here's an example. Find the area between z equals negative 1.20 and z equals 2.64. This is the larger area. So I'm looking for A for 2.64 minus the area for negative 1.20. So again, we're going to look at our table. We're going to look for 264 first. So here's 2.6 here. Here's 2.6 here. So we're going to count. So 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. That's 9959. So that's 0.9959 minus the area for negative 1.2. So here's negative 1.2 right here. And since my hundredths is a 0, I'm just going to go to that first column, 1151. And I'm going to go ahead and subtract that. So 0.9959 minus 0.1151, and I get a value of 0.8808. So that's the area in between those two z values. And again, that's using a standard normal distribution table. Okay. So determining other areas under the curve utilizes the fact that the area under the entire curve is 1. Okay, because remember, it's probability. Taking advantage of the symmetry of the normal distribution is also useful too. So notice that we use z-scores formatted to 2 decimal places after the decimal and areas formatted to 4 places after the decimal. So z-scores round to 2 decimal places. And 4 decimal places for the area itself. So again, this, this is using a left tail style normal distribution, right? So find the area underneath the standard normal curve to the left of z equals -1. So again, it's to the left. So we're using the table directly. So -1, that's right here, 1.1587. Again, to the left of z equals 1.18. So here's 1.1. Look for a hundredths value of 0.08. 0, 1, 2, 3, 4, 5, 6, 7, 8. That's 0.8810. Okay. Find the area between 2 z values. So something that might help is if you sketch the area first. Right? So here's my normal curve. Here's my mean, 0. Here's 1, 2, 3, -1, -2, -3. So I want an area between 1 and 2.7. So 2.7 would be right about here. 1 would be right about here. So this is the area that I'm looking for. So if I'm going between 2 z values, I find the area of the larger value, so 2.7, minus the area for 1. All right, so look for 2.7. Here's 2.7. The hundredths place is 0, so I'll go to the first column. 9965. 9965 minus the standard deviation for 1. So look for 1.0 here, 8413. So I'll go ahead and subtract those two values. 0.9965 minus 0.8413, and I get a value of 0.1552. Okay. Find the area to the right of z equals 0.94. Again, let's look at what this area looks like. Here's my normal curve. Here's 0. Here's 1. So 0.94 is right before 1. So I want this area. Well, this is to the right. This is a left tail style table. So I'm going to take 1 minus the area to the left of 0.94. All right, so look at my table. I look for 0.09 or 0.9, which is right here. Here's 0.9. I'm going to go find my hundredths value of 0.4. So 0, 1, 2, 3, 4. That's 8264. 8264. That's a value of 0.1552. 1736. Now, why is it important to practice finding areas under the standard normal curve for various intervals? Because again, it has to do with the probability. It's because the probability that z lies in an interval is given by that area underneath the curve, right? So for example, if I want you to find the probability that a z-score lands less than or equal to 1.19, then just use the table to find the area under that curve to the left of that value, okay? Here are some more examples, okay? This time, you don't even need to sketch it out. You don't even need to sketch it out, right? First off, let's look at each one of these. This is a less than or equal to, so that's going to use the table directly. This one here is greater than, so that's to the right of this value. So we're going to have to take the area to the left of this and subtract 1 from it. Here, take the larger value, the larger area minus the smaller area. Okay, and that's all using the standard normal table for these. Let's look at the first one. So looking at the first one, z is less than or equal to negative 2.15. Well, where's the area that says negative 2.15? So here's negative 2.1. Here's negative 2.1. Let's find 5, 0, 1, 2, 3, 4, 5. Here it is, 0.0158. Now let's look for this one. Z greater than or equal to 1.35. So I look for the area to the left of that. Okay, where's 1.35? Here's 1.3. Let's count. 0, 1, 2, 3, 4, 5. That's 9115. 9115. And I get a value of 0.0885. And that's just from doing, I mean, you can do this in your calculator and it'll give you the same thing. All right, next. This is the larger area minus the smaller area. So where's negative 1, 2, 3? Here's negative 1, 2, 0, 1, 2, 3. That's 1093 minus negative 178. So where's negative 1? Here's negative 1, 7. 0, 1, 2, 3, 4, 5, 6, 7, 8. That's 0.375. Okay, and let's see what that gives us. 0.1093 minus 0.0375. That's a value of 0.718.